And you'll see there's a good discussion in your textbook about the difference. But I just want to take a minute and quantify and discuss what a conservative force is. So it's an appropriate time for a definition. A conservative force is any force that does the same amount of work on an object regardless of the path taken. So when we're talking about work, we're talking about a force applied over some distance. So of course we're talking about a path. If you're moving some distance, you have to take some path to get there. So a conservative force will do the same amount of work regardless of the path that you choose. The most classical example of this is if you take a look at an object with some mass that is falling or being lowered some distance. So here's an object. This object is being worked on by gravity. It could be other forces as well, but gravity is definitely doing some work on this object. So it moves a vertical distance h under the influence of gravity. So we could ask the question then, how much work is done by the gravitational force in this problem? All right, so our definition of work is a force times distance. Our force is gravity. Our distance is h. And then we add in the cosine theta, where theta is the angle between the two vectors, the displacement and the force. In this case, theta is 0. So that cosine term, cosine of 0, is just 1. So the work done by gravity is Fg times h. All right. Now, if I were to move that object in a different manner, let's say I move that object, instead of going straight down, first I moved it over here to the right. So we went like that. And then after that I slid it back over to the left so that it still ended up in the same position relative to the original position. But we went to the right first. Okay. Well, again, gravity is doing some work on this object. And that applies over here as well. So I kind of have to break this up into two different paths, right? We have in this case, we have a path that's going on this angle to the right. We'll just call that theta. And then we have a second path going back to the left. So we have to do two paths here. So for path 1, we can calculate the work done by gravity. It's equal to Fg times this side. We'll just call that side d, the displacement, which is d, and then the cosine of the angle between, which is this theta that I've defined right here. Okay. Well, Fg d times cosine of theta, that seems like a trig identity. What we have right here is a right triangle. So if I take d, the hypotenuse, times the cosine of this angle, what side is that? Is that this side or this side? The vertical side. Well, that vertical side is just h, right? It's gone the same distance, h. So then we get the work done by gravity here is just Fg times h, which is the same thing as we have over here. So that's kind of interesting. But the question now is, well, we've only done the first path. What about path number 2? How much work was done by gravity in path 2? So again, we have Fg. In this case, we'll just call this side, I don't know, I'll call it x, which is the distance from here to here, the distance that it moved. Fg times x times cosine of theta. But in this example, x is perpendicular to the force. So theta is 90, which means cosine of 90, cosine of theta is 0. So the work done by gravity in this case, because the displacement is perpendicular to the vector, to the force vector, like we talked about last week, the work done is 0. So the total work done by gravity is just Fg times h. The same in both cases. All right, so this is an example of a conservative force. Gravity is a conservative force because it doesn't matter the path you take to get from point A to point B, the work done by gravity will always be the same. All right? So with that little tidbit of information, can we maybe think about some forces that are conservative besides gravity? Who can tell me, so we have conservative forces, we'll make a short list. We have gravity as one, we just met it. Gravity is a conservative force. Any other ideas what other conservative forces there might be? We met one other one. So if I were to write non-conservative forces, so think about this, you know, in conservative forces, your day-to-day life, all right, friction. Friction does work, right? Friction wastes energy. If I move, if I slide across the room somehow, I don't know, friction is slowing me down. I only go so far. All right, if I go this way and then this way, do you think I lost more energy to friction because I took a different path? Yeah, I mean, I was certainly contacting the ground more. There was a lot more heat being created between my sandals and the floor. There's more dust being kicked up. So yeah, that energy was lost. In other words, it does matter what path I take. If I want to have the least amount of energy lost to friction, then I need to take the most direct route between point A and point B. So friction is a classical non-conservative force. All right. Along the same sort of lines, air resistance. All right, air resistance depends on the path taken. Other forces that we've met, things like tension, things like the force due to a person pushing or pulling, engines, forces that are exerted by engines. These are all non-conservative forces. All right, most of the forces that we encounter are in fact non-conservative. But we're missing one over here. What are we missing over here? Spring. So springs exert conservative forces. In addition to that, the electric and magnetic forces are conservative. All right, which you'll encounter in Physics 222. Now, the reason that we make a designation between conservative and non-conservative forces, part of it's to put sort of these forces in context so that you know, all right, if you have friction, that means you're going to lose some of that energy. And in our mechanics world, we're dealing with mechanics right now. If you lose energy to heat, we don't have the ability to track that. We don't know how to count how much energy is lost by heat at this point, or how much energy is lost because I created dust or something like that. We don't know how to do that. So in our mechanics world, when we're talking about things like conservation of energy, which we'll talk about more today, we can't really account for that stuff other than saying that work must have been done by those processes. But conservative forces are special. These forces, because of their conservative nature, we can write these terms in a special way. We can associate each of these forces with an energy term, and specifically we can associate them with a potential energy term. And we've, of course, already done that for springs. You've met the potential energy due to a spring, 1/2 kx squared. That's just the work done by a spring, right? So we're talking about conservative versus non-conservative forces. And what we introduced this concept with was what I said was that work done by a conservative force doesn't depend on the path. What that allows us to do then is have a special equation, a special formula that we call potential energy that applies to that force. So just like we met potential energy due to a spring, we're going to talk about potential energy due to gravity because it's a conservative force. When you get to physics 222, you'll talk about the potential energy stored in electric and magnetic fields. Okay? But we can't associate potential energies with these things. We can only just talk about the work done by these forces, force times a distance or something like that, but there's no special 1/2 kx squared for friction. Okay? It just doesn't work because those values depend on the path taken. All right, so let's do another little example showing the difference between conservative and non-conservative forces. So we've kind of done this already. So imagine that you take a box that has some mass, and you move it along this path. Starting from here, you go down, you go to the right, then you go up. We know that the force due to gravity is always acting on this box. It's always pointing down. So what I want to know what is the total work done by gravity. Right, so I'll subscript that like I did before on that box. Anybody want to take a guess what that is right now? Off the top of your head, just looking at that without doing the math, without doing any math. What do you think it is? It's 0. Good. All right. So with this, another way to sort of look at conservation of energy or conservative forces is that if your starting and ending position is the same, then there's no work done by that force. Now we could actually do that calculation. So let's do that really quick. If we define 4 different paths. So this is the first path, the second path. Oh, that's a bad way to define it. The first path is moving across the top. The second path is moving down. The third path is moving across. And then the fourth path is moving back up. So we're defining these paths as the box moves around in this loop. All right, so we can calculate the work for each of those paths. So let's do that. Work over path 1, force times the force due to gravity over the displacement. The force is perpendicular to the displacement, so the work is 0. All right, just like in the example we just did. Over path 2 here, force and displacement are in the same direction. So we get Fg times the displacement. We'll just call each side of this box d. So the side, this is we'll consider it to be a square with sides d. So the work over path 2 is just force of gravity times d times cosine of theta. The angle between the two, well, that's just 1, because theta is 0. The work done by gravity on path 3, again, the displacement and the force vector are perpendicular, so the work done is 0. Finally, the work done in path 4 looks very similar to the work done over path 2, so we get force of gravity times d times cosine of theta again. But this time, gravity is pointing down and our displacement vector is up. So theta is 180 degrees, which means cosine of theta is -1. So if you add all these up, you get force of gravity times d minus force of gravity times d. So the total is equal to 0. Yeah, Shane. All right, so this is, I mentioned that, well, we talked about this last Wednesday, right? About, gravity doing negative work. And it seems very strange because, well, gravity just wants to pull the object down. It doesn't ever push it up. It's always pulling it down. So it's strange to think of the concept of work being negative. But you have to imagine when this box moves up, there's some other force acting on it to make it go up. Okay, so we're not looking at all the forces here. We're only considering the force due to gravity. So by this term being negative, what we've really done is given gravity the ability to do more work. We've sort of added some energy to the system, which gravity then can later use to do work and pull it back down. All right, so when we have a negative term, we've added work to the system. All right, so the sign is sort of tricky, especially when you think about gravity. But remember, our original definition was if something had a negative term for the work, that means it's putting energy into the system. And you can take that out later in some other form or something like that. Yeah?
So if you have higher negative work, then does that mean you're making more potential energy?
Right, so in this case, because we're moving this box up and force of gravity, or the work due to gravity is negative, what we're doing is we're storing energy in the form of gravitational potential energy. Right, so that's what we're coming to. Is we're taking this work, because it's negative, we're storing that in gravitational potential energy. So we're giving gravity the ability to do more work on that box. Any other questions? All right, so let's turn this picture on the side. That was like a side view. Let's look at a top-down view now. And imagine that a very similar picture. This is the top view of a similar box where this guy is being dragged along the floor now. Okay? Now in this picture, assuming we have some friction, which is a reasonable assumption, the motion of the ball is always counterclockwise, or the motion of the box is always counterclockwise. So again, we have these arrows. This will be side 1, path 2, path 3, and then path 4. We want to ask the question of what is the work done by friction? What's the total work done by friction here? Do you think it's going to be 0? Okay, heard a couple of yeses, a few no's. Let's do the calculation. Okay, we have to take into account all 4 sides. Now, in this case, the box is always moving counterclockwise, which means, and friction is opposing the motion. So the force due to friction is always going to be sort of in the opposite direction. Like so. So we can calculate that work. Over path 1, we have work done is just the force times the displacement. Again, the sides this is a square, so we're going to have sides of length d. So the work done by friction is the force of friction times the displacement times the cosine of theta. Force of friction is opposite the displacement, so this becomes, the theta is 180 degrees, which means that's -1. So what I get is negative F times d. Path 2, force of friction is still there. I'm still moving a distance d. Cosine of theta is still 180 degrees. The force of friction is up, our displacement is down. So theta is 180 degrees, so this is still -1. Over path 3, you're going to get the picture here. It's the exact same thing. Friction is to the left, the displacement's to the right. So we get force of friction times d times -1 again. And finally 4, force of friction times d times -1. It's the exact same thing. All right, so the work total is -4 times the force of friction times d. So it's not 0. All right, and so in this case, we've added energy to the system in the form of heat, or we've taken energy out of the system in the form of heat. All right, so we sort of put the work done by friction went into heating up the box or heating up the floor or moving some dust particles or something like that. Okay, but we sort of lost that from the system. It was put into the system, but we don't get to get that back later on because it's a non-conservative force. All right, so the difference is we had up here we had work due to gravity. It was negative over this path, and I said that energy was put into the system, and we could take that out later. That's because gravity is a conservative force. Here, the work of friction is always negative. We're putting it in the system, but we can't get it back later because it's a non-conservative force. It goes into heat, it goes into something else where we can't get that back in the form of mechanical energy. All right, we don't know how to get that back. Okay, so that's the difference between conservative and non-conservative forces. So there's a couple of problems on your homework where you're dealing with these. Look at the different paths that the object's taking and calculate the work done. And this is all you're doing. Distance, force, and then don't forget the angle is important.